We are here downstream, where I'm sitting now, downstream of Switzerland, at the end of the River Rhine, sort of basement of the whole system. And what I want to talk to you about is a landscape view to reduce chemical pollution. And I feel very welcome with you. And this is a picture of the River Rhine from outer space. The Netherlands you see here is sort of from top to bottom, from west to east. Have you ever wondered where exactly the Rhine River flows in the North Sea? These sun-glint photos show why the answer isn't that simple. We have a lot of water down here, and this is from a German astronaut. What I would like to do is to start with conclusions, so that you can trace back where these conclusions came from, and that you are on your chair fastening your seatbelts. It's to start with, it's good to do Water Framework Directive, that's the abbreviation, and to liaise, for example, with you on the hydrological basis that you see to the right for the River Rhine. It's good water quality is vital, and we need solutions to protect and restore it when needed. But what kind of solutions? In a sense, the basis, I call the Water Framework Directive a sort of brilliant piece of legislation, because it's nature-based because of these hydrological principles, but we can improve its practices. And improvement of the practices will be part of the talk. And we need and we can combine disciplines for safe and sustainable by design river basin care. So the conclusions are there. You can go to sleep, or you can try to track where they came from. I hope you do the last. What I will do is to bring you a quick tour of all kinds of disciplines with whom we work together. The quick tour on the societal uses of water, scientific principles which are a bit hidden in the Water Framework Directive, regulatory basics, where they came from, what we can use, produce some risk maps in colors and stuff, and to explore with you the solution space to improve the practices. There is so much to tell that it's only snapshots, but I do my best to explain them to the best I can. And I come back with you, with whomever wants to have contacts later on after this talk if needed. So let's go. You sometimes see solutions markings in the pictures, or sometimes other markings in the pictures, just like here, solutions. That's where the project, together partly with colleagues of you, happened. So this is the Rhine Basin, which is the blue part. I must look at whether I can put, how do you do this? Annotate, there we have it. Spotlight, is this working? Yeah, here, there you have the River Rhine, the catchment, the whole basin. And in fact, we are hydrologically one with you at Eawag and Switzerland. What you see here is we are densely populated. The population density is in gray. And here we have the land use is that there's lots of land use and all kinds of different agriculture. And I can show you various of these maps, but in summary, we are just likely drivers of change. Mankind is a driver of change. Now I must look whether I can go to the next slide. I'm messing up. Okay. Let's see what happens. Yeah, I will not do this anymore. The annotate must be gone, otherwise you keep on seeing these things. Sorry for that. Okay, the lessons learned are from the past. Of course, Schweizerhalle in Switzerland, November 1, 1986, a big incident in a chemical factory out there. It caused the emissions of a lot of plant protection products. On the bottom in the middle, there's tonnage of stored chemicals. There's only a small list on the x-axis, the list is longer, but the tons of emitted to the Rhine is in the top graphic. Lots of chemicals were in the Rhine, and the River Rhine was dead for 400 kilometers. And the interesting part in the paper by Mr. Giger, review on that a few years later, is that you see an emission profile and an effect profile. On the top right graphic, you see that the amount of chemicals over time, and you can also interpret that as distance later on, that there is a sort of prop flow of chemicals going down the river. But the interesting thing, that's for the chemists amongst us. But for the ecologists and the ecotoxicologists amongst us, these things caused a response in definite toxicity. Bioassays being executed at various spots in the Rhine showed that this indeed caused a lot of stress. And of course, you saw the dead fish also along the borders of the Rhine. So that was already a big lesson. Collaboration on a basin scale was needed according to hydrological principles. And if you look at the data and current problems, you need a lot of expertises. Hydrologists to look at the fate of what we throw in the river. Geographist specialists to look at land uses. What kind of land uses and what kind of fingerprints do they emit? Environmental chemists to look then at the concentrations downstream, even if compounds are broken down over time. An ecotoxicologist looking at impacts. And a lot of stakeholders who drink the water, who want to use it for feed drenching, cattle drenching, or for spraying their crops. Various needs by the stakeholders. And all, we need solutions for all those solutions of all those chemicals. And I think in history, it was also a co-trigger for the Water Framework Directive to be developed in the way it was, a hydrological system-based approach. And the key needs that we have are top science, on which we hope to contribute at our site with Eawag and RIVM and others. But we also need practical support. And because water quality is protected by many, it's monitored by many, and it's finally restored by many. Let's go. What happens then? The Rhine, micropollutants and society. Recent data from Riva Rhine to show how difficult the problem is. What was developed for the area in Lobit where the Netherlands, the Rhine enters the Netherlands, but also for these other spots, the drinking water producers wanted to make a metric for the drinking water clean-up intensity. The metric is called a bit different, but that's what it does. How much intensity do we have to clean it up before we can drink it? And then you see that over time, the x-axis here is time, the vertical axis is this intensity. There is a trend of temporal variability, but also a rising trend. So the problem becomes more complex to make drinking water. And how does it look? If you only look at a very few compounds over time, which are measured out of the many that we produce, then you see this graphic from left to right again. Over time, the amount of plant protection products in the water system at Lobit. And here for industrial chemicals and things that you use in your household, all the colors are a different compound, and they change over time at this single sampling station. I could make more of these, but there it's only meant to say the problem is increasing to produce drinking water, and it's diverse in space and time. The Rhine micropollutants and society, it's only drinking water is only one of the surface water users. So there are multiple stakeholders with experiencing the same type of problem at many places in the area. Environmental chemists, amongst you also, have found an immense variety of unintended mixtures in these surface waters that we want to use. Time effects and spatial effects are abound, they are everywhere. And what we see here, and now we turn from what we do to what we would like to do probably. So far, we are grouping them according to law. In the previous slide, you saw plant protection products and industrial chemicals. That is a sort according to law. But what I would like to see thinking about is also opportunities to do different groupings via mode of action, but also, for example, via land use of origin. Because if you are aware of the important land uses that emit a fingerprint of chemicals, then you might think of handling that whole land use as a source of multiple chemicals as a solution. Or, as for the drinking water, via removal techniques. If you implement a new removal technique, it doesn't look at the law under which a chemical falls, it looks at the characteristics of the chemical for the breakdown or the removal. And there is also a nice opportunity for historians, if we have long-term data, what things in the past for the solutions worked? What has made a lower distance to target? And the target is the toxic-free environment, which is now in the policy making. Which programs of measures did work? I think it's very nice to have a look back also in time. One of the things that struck me working in this field a bit is that this is the history. Factories, companies, they think there is a chemical use in society and they make a plan to produce a chemical in blue. Then they design it beautifully, the chemical is doing what it should do, etc. And then we react. A chemical dossier is being made and we are usually allowing a chemical on the market if the risk quotient, the RQ, is below 1, and the risk quotient is the PEC over PNEC ratio. PEC is predicted environmental concentration under foreseen use. The PNEC is the predicted no effect concentration. If that's below 1, the conclusion is safe use and the chemical is allowed on the market. It's a sort of black and white, but in this case, blue and red thing with a borderline thing at risk quotient is 1. Prevent. The other one is monitoring. After the event of allowing a thing on the market, you do the monitoring, and then the risk quotient is called measured environmental concentration divided by EQS, the environmental quality standard, which is more or less similar to the PNEC. And again, it's similar. If it's beyond 1, you have to restore. So in colors, you see the principle. But what struck me was in fact this one. The approach is a sort of reactive one. Somebody designs a chemical and wants to make it and wants to produce it, and the whole society and the scientific societies are filling dossiers and doing all these kind of things to look at these two colors. Is it blue or is it red? Prior to the act or after the act, and we have a lot of stuff to restore. That will be part of the later part of the talk. So it's reactive. Please keep that in mind. What is our mandate, in fact, to do that? I look back in the real things behind it, where my mandate for my work would be, and that starts with, probably with the Sustainable Development Goals, of course, but for the EU, it starts with the Charter of the European Union. There are 2 key articles for us out here. EU nations should protect human health, full stop, Article 34, I guess. And the second one is EU nations should protect environmental quality, comma, or if needed, restore it according to the principles of sustainable development. These 2 things are a sort of generic mandate, a sort of umbrella above everything that we do. We want to keep the water clean, or we want to restore its quality because of these 2 things. And then you have all these laws under this umbrella. To the left, the prevention, REACH for industrial chemicals, plant protection products, biocides, and what have you. And the other way, restore if needed after the monitoring. For example, the Water Framework Directive and also the soil strategy is now upcoming. And that's a sort of balance that European countries can use, better prevent to avoid restoration, but if needed, restore. So this is the legal framework under which we work. We can use prevention, we can use restoration, and they are in the balance. Now I jump from the mandate to the history of risk. The history of risk, the whole thing is risk-driven. If there is too much risk, it becomes red. But if you look here in the history of risk, risk is always defined as a sort of a product of the likelihood of something nasty happening and the degree of damage of something nasty happening. And the oldest history is in the book that you see to the right. The book is called Against the Gods, and it's called that way because people before the invention of the word risk thought about heavens coming down on them because of the gods. But the oldest history developed statistics on the basis of, and that's surprising, normal distributions of data. For example, on life insurance or trade and sinking of ships, those kind of things. That is the oldest history of risk assessment. And that has a nice link, a historical link, with environmental chemistry and ecotoxicology. And now I ask you to dive into the deep a bit in your statistical mind and go from the history of the mandate in regulatory sense and the history of risk to what we are doing indeed now, and what Ahmed already told about species sensitivity distributions. The risk-related disciplines since the old book, old history of risks, are risk is quantitative. It's not blue and red or black and white. It's quantitative, and it's working as follows. Environmental chemists in blue found out, and I already showed that exposure concentrations of chemicals on the x-axis are distributed, and that's the hump with the blue exposure, the PZ curve. Exposure is distributed in space or time. Ecotoxicologists have found out that all animals are unequal, and the sensitivity, the green marked line, are distributed. And the statisticians amongst us in the past have found out that this delta area, this gray area here, underneath, you can calculate it by mathematical formula. Delta is the expected risk for an area or for a period. For that distribution of exposures, this hump, or that across species distribution of sensitivities. Now a more bit refined, the risk-related discipline is quantitative because of the following. In the 1980s, people in the US and Europe, they both observed independently, if I understood the history well, that species sensitivities that you see here to the right in this graphic, all kinds of species have been tested in the lab, are log normal distributed, which means that their cumulative distribution function is a sigmoid, just like here. And the beautiful thing that they found out at that time already was that that has two uses. The first one is setting safe standards, that if you take on the y-axis a certain level that you say this is the maximum, that you can read out for every chemical the HC5, the hazardous concentration for 5% of the species, also known as the opposite. 95% of the species is protected if the concentrations remain in this area. And that was assumed to be representative of a sort of safe use. The other way around in red is now appearing. If you then have an ambient concentration, which is out here on the x-axis near the value of log concentration is 1, then you can derive what they call the potentially affected fraction of species. Here, 1, 2, 3, 4, 5 of the species tested. There were 10 or 12 species tested. 5 of the 12 tested the PAF, potentially affected fraction. And of course, if the concentration in the environment increases, the number of species that suffer is going up. That was a beautiful thing, and they call it a species sensitivity distribution. An immediate link with the word risk as a quantitative historical, the oldest mathematical model in risk is this one. And if you then apply that risk principle to the field and count here in hundreds and hundreds of sites in the Netherlands on the y-axis the number of taxa per sample, and you have on the x-axis the toxic pressure of one chemical or the mixture, I'll come back to the mixture in a moment, then you see here the top right part is empty. And that means mixtures limit biodiversity. There is even a sort of seemingly straight line or a bit sharper going down. Mixture toxic pressure matters. I'll come back to that later in the talk in a sort of nuanced idea, which is also being developed by a colleague of yours, Nele. Risk-related disciplines, what can we do with these kind of things? The quantitative principle. We already have now 250,000 people who have been doing a test with a species and a compound, and they stored it in big databases. We were able to make this SSD curve with this dual use for more than 12,000 compounds. For the EU, we have the WISE database on exposures. All countries report their data to the WISE database, so we have exposure data. And for the Netherlands, we did an extra step, and we have 44 million monitoring data lines for hundreds of compounds. And then you can easily foresee that if we make a bit of programming, which we did over the last years, we can do this overlay trick of the green and the blue exposure distribution and the green SSD, and we can make a sort of risk mapping. So now, fast forward, is this a nice technique to be applying, and what can you learn from it? And then you see here a bit of the River Rhine again, but the whole of Europe around it, a quantitative risk map for the risk of mixtures of chemicals for the whole of Europe regarding ecosystem integrity. So the multi-substance potentially affected fraction ranking is the color scale. And as you see here, the quantitative risk map is based on, for every chemical that we found on this overlay plot. And then here the Netherlands is not the best country on earth in regarding mixtures, but Sweden, few people, lots of water, is of course more blue. It sounds, this picture looks reasonable from a point of view of what most people expect. But it's at variance with the EQS, the environmental quality standards in the water system, which is okay or not okay, the blue-red thing. In 2012, probably this was even the reason for starting the call for the project solutions. Sweden was the worst country in the European Union regarding water quality, and I didn't believe that, and I think the European Commission also didn't do that. It means, in fact, this red color means, in fact, that the water managers need diagnostic attention everywhere. Why is that? In this case, for Sweden, it was mercury in the sediment, which transferred via the food chain into fish and finally into man. And after 60 years of eating Swedish fish, you wouldn't be completely healthy anymore, likely. That's what it means, not anything with ecosystems. So the picture to the right is intuitively correct. It's based on every data that we had in these thousands and thousands of data points, and we could proceed on that. It is a help to prioritize risk management across the water boards, and you can refine that. That's on this map. This is an interactive map which you can find on the internet, and you can zoom into your street even. Then you see all these nice colored little balls changing in shape and size, but you can find your own water body in the Netherlands and see whether it's polluted for all the monitored chemicals together. So again, the multi-substance potentially affected fraction. But that's not the question. The question is, what should we do about it? So it's not only place, but also the group of the chemicals. And that's what we do here. You can do some diagnostics by taking out all chemicals except for this one upper left. It's the pesticides. And the pesticides, if you come to Schiphol Airport, which is in the western part of the Netherlands, the red area in the upper left graphic is pesticides. The red in the area here is pesticides. And the other maps, this one is about metals. I can see that from a distance. Here is a lot of smelter activity in the south. And the other ones are from other groups. So diagnostic, you can disaggregate. First, you look at place where it is. Then you look at group to prioritize your management focus. This also allowed us to liaise to multiple stress analysis and ask ourselves the question, oh, these colors are nice and it's a predicted impact and a nice color range, and red is of course a warning sign. But now we use the same scale to merge with the occurrence of species, the quantitative relevance of mixture toxic pressure MS-PUF. And what you see then here, trained on all the river ecological status data of Europe, we merged all the multi-stress data, including the mixtures. And what we found is that on average, mixtures, the toxic stress, are for 26% on average responsible for changes in ecological status, trained by 1800 plus compounds in this case. So the key word here is, at the present time, on average, chemical pollution is a limiting factor for ecological status. And what that does mean is the following. First, if the ecological status is affected by chemicals, I wouldn't like to drink it myself. So then the ecosystem is a mirror of what's also unhealthy for me. It's a sort of warning sign. But the second thing is chemical pollution, if not addressed properly, can be a hidden cause of failure to reach good water quality status. You can do whatever you like in remediation of any stressor at all, but if this is a hidden factor limiting ecological status, you will not succeed. And the task coming from this picture is to characterize chemical pollution in full, not forgetting any chemical that you might encounter. Mixtures matter. And that was what we found out. Now we go from Switzerland and Europe downstream to the Netherlands again. Mixtures matter in the Netherlands. In this picture, you see that we have a task to go. 1% of the Netherlands is in good status according to the water quality procedures of the Water Framework Directive. We are monitoring about 150 of the potentially 350,000 compounds that are in trade globally. We monitor 150, and even with those 150 here in the bar graph to the right under, you see that only 1% of the Netherlands is of a good water quality for these specific compounds. And that works via the one out, all out principle, OOAO. 1% of the water is in good quality, which means that at least one chemical is disturbing here within the red area, causing the water quality to be insufficiently good. And on the map, you see just a red hydrology of the Netherlands. So we have something to do because the deadline is 2027 to have 100% good water quality, 99% to go. So I'm a bit nervous on that. 2027 expectation. Why am I a bit nervous? Is that recent verdicts of the European legislature, the courts, they will likely grant any person who fights into a permit that the no permit situation will occur for any societal activity that might extra pollute the water. So it's very likely that the whole of the Netherlands, for these numbers, is going to a full stop for house building, for whatever vital things for humanity also. So going from 1% to 99 or 100% good water quality, we need some action. Compile the science, the regulatory things, the practice, etc. Concrete curing. Can we make some curation of this whole system? Or are we stuck in the mud and are we lost? I don't think we are lost. And that's the result of a project which followed immediately after the Solutions project, what I could call Solutions NL. In the logo here, it's called the Knowledge Impulse on Water Quality with this logo. But what we wanted to do is to work together with the water boards and the drinking water producers and the provinces to make something which is very useful, to go from the 1% to near 100% if feasible. And the basis, it must be logical in the regulatory sense, in the scientific sense, and in the operational sense. And therefore, we made a website with a lot of tools. And I call them here, to be short, lookup tables, the mixture toxic pressure calculator, a bioassay battery standard, etc. And to the left bottom of the graph, you can see the name of the website. And if you use the website and use Google Translate, then you have an online translation of the website, because I'm sorry, it's in Dutch if you just press the buttons, but you can translate it online. And they call it the key factor toxicity. Key factor because it's a limiting factor. I show you 4 or 5 key principles which are helping us forward. The first one is that the Water Framework Directive Principle 0, I would call that. Any stressor now and in the future is of interest, because if that stressor is making the water quality bad, we want to counter it as society. We want to drink the water, we want to have the cattle drinking it, etc. So we want to have clean water whatsoever. All chemicals are on the ballot. all scales. And what you see if you look at the water framework, then you see the brown bar is Europe as a whole. There we have a list of 45 priority substances. That's the name. But in fact, you can see that the Water Framework Directive is a cascade of coordinated responsibilities. The brown is the European scale. The priority substance is about 45. The European Commission helps to organize European-wide environmental quality standards for those. Within that, you can see the River Rhine, for example, or the River Danube, with the word river basin specific pollutants. And of course, then there is a sort of basin authority, the collaborated countries, International Commission for the Protection of the Rhine. And why did we stop there? Because that's the observation. Why did we stop there? Why isn't there something like that on the sub-basin scale with environmental quality standards for specific pollutants at the sub-basin scale, or even at the local scale, the water boards? And then you see here the sub-basin and the water boards. And the hydrologists have even said for now 10 levels of this kind of nested approaches, but that's what should happen. And I call that a Matrushka style principle. Lower levels of interest need be added. If I use in my backyard some strange chemical, which is on non-list at all for my garden for some reason or another, and then all the fish are dead because in a ditch behind my garden, and everything is dead because of that strange chemicals, that is a specific chemical which we should take into account on my local scale. If it's nasty, we should counter it. So it's an all chemicals principle. The second principle is shown here. Everybody who is working with the Water Framework Directive knows this abbreviation. It stands for drivers, pressures, status, and impacts, and finally responses. And the history is, of course, that if you go to the left and you have a dirty, not okay water, and you want to move to the right to a clean water, then you can follow this system. Analyze the drivers, which is sort of land uses. Pressures is the leaking points, the emissions. Status is how is the water body in itself, the concentrations, etc. And the impact is, do you see dead fish? Is the biodiversity okay? But the key part here is the response. And we made this graphic, the DPSIR is always used from left to right, usually. First the driver, then the pressure, then the state, then the impact, then the response, as if it is a sequence. And we just state, no, it's not a sequence. Anything that goes from any of these corners is valuable to derive your response and move to the clean water body. So in all corners in the website, in all corners, we made a sort of toolbox for operationalization. For example, for the pressures, if you see a land use driver, we had here the pressures, a lookup table from land use to the chemicals. A potato field just has a fingerprint of 5 typical pesticides, and a wastewater treatment plant has another lookup table result. Another example here, a lookup table from the chemicals. If you know the chemicals, you can find the bioassays which are sensitive to them. Insecticides, I would know that it would be a definite water flea tests. Now, at every corner, there is a suite of tools that you can use. But the final thing is that water is only getting clean by the good responses. And the good responses is a good diagnostics. So the blue in the middle is the most important part. The other principle is nuance, and I just talked to Nele about it also a bit. And you've seen this graphic already with the monitoring data. If the upper right corner of a monitoring database with a stressor on the x-axis and the ecological status or biodiversity on the y-axis is empty in the upper right corner, then statistical theory says that the X factor is then the limiting factor. And here it's toxic pressure. The other dots out here can occur underneath this envelope curve because, this red dot here to the lower left is of course low, not because of toxicity, but because of pH or temperature or another stressor. So this kind of work is the basis to derive nuance. It's not necessary to have good in blue on the x-axis or failure to reach good in red as good and bad, but you can nuance it. And this is what we designed for that. And I think Nele is also working on that. The water quality standard is still there. The difference between good and not good. The mixture limit is at the top right of the green bar, which is the same as in the ecological status. There is not yet a response. And then the other ones are, of course, moderate, high, and very high toxic pressure. Those are then the reason to be able to prioritize. And then protection, the role of protection is the EQS remains to be a ceiling. There is no reason to remove the principles of the Water Framework Directive. To restore, the EQS is again the target. I don't touch the principles of the Water Framework Directive. The only thing that we propose is also that you have nuance. If the x-axis is going to the right, you are able to broom, so to say, the staircase from the top. Worst sites first, and worst chemicals within sites first. And that brings priority in restoration efforts. The better you can spend your money on the red rather than the orange, rather than the yellow. And we hope that this brings forward the speed of restoration. Now we come to the Water Framework Directive principle number 3, which is classification and diagnostics. Everybody working in the classification in the Water Framework area or directive area is that everybody is doing all these things of classification. We have to report to the national authorities and then to the EU in the blue and red bar idea. And that works as follows. Many data on ecological data are collected for different species groups. And the same holds for the physicochemical data and the specific pollutants, what they call. And here you have the chemical status with the priority substances, chemicals that occur at a European scale. And here you see that classification is from left to right going to a sort of summary statement finally. But what you do when you have a summary statement, you lose insight in what happened here. You can summarize a lot of data in this kind of things. 35,000 water bodies, 33% are good status, 67% are in a bad status for a few chemicals. That was a study we did some time ago. And you can do this mapping. Hey, you recognize the mapping of a moment ago with 100% red in Sweden. And my statement here that principle 3 is the opposite. Classification is summarizing for reporting, but diagnostics is the opposite. And I'll show that here. Imagine that you have 100 water bodies and you have a few blue, a few green, so no ecological response yet, a large part of yellow in which the slight ecological response, bigger and very big ecological responses. So 100 water bodies with different status. And then diagnostics is doing per site, per hydrological unit or per land use, the opposite. And you don't read the letters because I just swapped the picture. It's disentangling this final color scale for every water body in its causal factors. And that's what I do here. For example, you can find out which of these chemicals, priority chemicals in the EU, are on the list, which are beyond their EQS. You can do also that for the specific river basin specific pollutants. And what I added in the Matryoshka puppets, you can also do that for the local chemicals. And of course, the limitation to the ecological status is by the aggregate, the sum, that's the mixture of concern. River basin specific pollutants plus priority pollutants plus the local chemicals of your scale, those things are the mixture of concerns for that water body. And only by doing this, you get grip on the diagnostics. Classification is summarizing, diagnostics is understanding. The website then has two major tools apart from all these lookup tables and all the other little nice tools and principles. And I will dive into that for the time being to make it, to help you have a degree of belief in that. Component-based methods start with the name of the component in a mixture and the concentrations of that. So that website that I show contains a beautiful calculation tool in R Shiny. R is the calculation motor and Shiny is the thing that you see on the screen. It's very user-friendly. The input is the monitoring concentrations or even predicted concentrations. If somebody asks a permit, then you have predicted concentrations. And the output is numerically, but also in the 5 colors that I showed in the previous graph, toxic pressure for every compound, according to the SSD, the toxic pressure for compounds group that you like, for example, insecticides, or the total mixture toxic pressure. So you can aggregate and disaggregate whatever you like. Is it valid? And this graphic, that scheme of the 5 colors, is it valid? Yes, it's valid. This is a big study of all the rivers in Europe. These are 30,000 dots spread over this area. On the x-axis is the toxic pressure. On the y-axis is where is the ecological status. And the black diamonds are the P95 of this big data set. This is the 95th percentile. And you see all nice red lines. For the big rivers, there were fewer data and it's a bit messy because big rivers are very diluted, so they might be a bit strange. But in all cases, there is clear evidence that mixtures limit the ecological status throughout of Europe. So interpretation of component-based methods, you can easily calculate it massively and it makes sense. Higher values imply higher problems for your ecosystems. The other one is quite new. Effect-based methods have been with us already also 20 or 30 years. And the principle is as follows, and I dive now into the quantitative interpretation. But let's imagine that we have 350,000 chemicals in trade and we want to control and know them. Now imagine that we have, for example, 10 mode of action, insecticide, herbicide, and what have you. So then you design 10 bioassays in a sort of battery, and that you see on the bottom of the graph. Lots of chemicals out there. You have a few test species or cell lines, and then you determine the quantitative response. The website contains a standardized proposal for a standardized bioassay battery, and the interpretation, and that I'll show in the next slide, is quantitative. What you do is to sample some water with an unknown mixture, run the battery of bioassays, and then look at the output that's in the next slide. What we did here, to show you the next slide, was to collect the available data for the Netherlands. A lot of work, 8,800 lines with a place, a time, a bioassay, and a value, but we did it. And this is what comes out. Effect-based methods to the left are often in this scheme of the black and white system. Imagine here now on the x-axis that we have 20 about places in the Netherlands, and we calculate a mixture toxic pressure with a calculation tool. So this is the stress level from left to right. And the 5 is big because that was the threshold which we use for the EQS, the quality standard. So blue is safe and beyond blue is not safe. But the bioassay effect level are here, but the left graph is standardized via effect-based thresholds. So the value where below and beyond the level of Y is 1. So this would be blue and this would be red. And you see no relation between the measured chemicals on the x-axis, the toxic pressure of that mixture, and the response of the bioassays. But to the right, just remove this threshold thinking again. Here we have the quantitative mixture toxic pressure. Here we have on the y-axis the bioassay effect in a quantitative sense without touching anything, just what came out. And you see a beautiful relationship that below the 5th percentile, it should be safe and there is no response in these bioassays. The higher you go, with a sort of safety space here between 5 and 20, but beyond that, this set of bioassays is showing a near a dose response relation type thing. So effect-based methods can trace things that you cannot see with other methodology. So I have a great degree of belief in developing these kind of things. Why is that? Again, a validation. If you do for all these red dots out of these 8,800 lines, an assay in which you do both the bioassay response level in this case and the ecological status in the field, in this case for invertebrates, a definite field test as a bioassay with the question, is the signal diagnostics? And then again, a lot of data points with the P50 is the orange and the 95 percentile is the red. You see here very clear relationships that if the bioassay response is increasing, that the ecological status is limiting. Again, the upper right corner is more empty. Now, the new thing in the Green Deal chemical strategy for the sustainability is the toxic-free environment. And as you see here and in all the other graphs, all these colors, we are not yet there. And we developed a sort of a website with a lot of tools to help the thing forward to the toxic-free environment. Diversion should end. We had concrete curing in the beginning, and then the other end of the road, diversion ends. But sorry for that. I found this in London. The said Murphy. So there might be a Murphy's law that we don't reach the final goal, but let's go. Let's have a look. The toxic-free environment distance to target, could that be of help instead of the red and blue? In addition, by the way, to the red and blue. What you see here in the background, I made it transparent, are the raw data. But of course, from left to right on the x-axis is years of management of metal pollution at the landscape level. On the y-axis, the red and the blue is the Water Framework Directive coloration. So everything is red from the beginning till the end. But if you then say, I use the calculation tool to have the nuanced view, then you see this beautiful downward pattern. I checked for the high and low points, and that relates to the weather conditions. So if you have a very wet or a very dry year, the amount of runoff from your land use is of course varying, and it dilutes more or less, and then you get another concentration. But management worked. There is a serious improvement of water quality, and the distance to target, which is the vertical distance between the line and the blue in this case, or the line and the green, the distance to target is just a decreasing metric. So far, the last slide showed a reduced distance to target to the toxic-free environment status, which is in the Green Deal. All the available methods, they help, but time to 2027 is short. And the options to improve of that are that we, of course, will say, please use the website, please use the tools, etc. But I come back to one of the things which were also in the talk, proaction. Why did we have the whole system in reaction mode? Somebody makes a chemical and we have a job to fill a dossier and evaluate. So let's go to the other one. What two proactive motions do we have? Time till 2027. Step one, and that's what Xenia also asked me to tell a bit about. Proactive, go in the field. Talk with the people who are active in management and protection. Scientists liaise to more practice people. What we did here prior to even think about the website was go in a tour around the Netherlands, have 12 roundtable talks with a lot of water quality practitioners, and we collected 189 practical questions, part of which we never expected would exist. But the top 3 of the serious problems which we teased out of that roundtable meetings, the first one was super surprising. The Water Framework Directive, aimed at good water quality, limits monitoring because people just in practice say, oh, we are already red, we want to solve that, prior to measuring more. The Water Framework Directive limits unintentionally the management. We invested a lot, but we remained red. And the Water Framework Directive limits diagnostics. We reported the status, we classified, we were ready, and we had no time or options to prioritize further activities. So 3 things which are blocking as a sort of unexpected side effect of the Water Framework Directive brilliancy blocking the progress indeed. This was proactive approach number one. Go talk with the real actors. Number two is, of course, a very big change in the Green Deal. Safe and sustainable by design is a key word in there. Why, if we would now make a chemical, why not make it safe, non-toxic, and sustainable, low carbon footprint, etc. by design? Make safer chemicals and safer products. That's in the law, that's in the Green Deal. This presentation I hope that this presentation will help you to also think about safer city design, safer industry portfolios, and safer landscapes. It's finally the landscapes that emits fingerprints of chemicals. So a proactive design of all the levels in which we can put our hand on. Will it have success? I hope so. This picture shows that to the left prior and to the right after some management, that the chemical footprint would reduce. We hope that that happens. We have techniques to do that. And indeed, over the past, on the x-axis, you see for the River Rhine. And now we are back on the River Rhine again, because we are living on that, you and me. From 1998 to the year 2008, we had nice numbers, and you saw already the chemical footprint going sharp down because of the correct measures taken against this group of compounds under study. So I hope you found back during the talk the conclusions which I just repeat. It's good to do the Water Framework Directive and liaise with you and others on a hydrological basis, chemists, ecologists, historians, what have you. Good water quality is vital, and we need solutions to protect and restore it because we want to drink it. Put it for the cattle, or spray it on our crops, or swim in it. The Water Framework Directive, if I do close reading, it is brilliant. It's the only, almost the only legal entity on Earth in which the natural boundaries are the principle to derive it. And therefore it shall work if we do it correctly. And we need and can combine all kinds of disciplines for safe and sustainable by design river basin care, from designing new chemicals to designing cities and landscapes. And here we are back. This is me asking you for questions if you have.